Hi there, Pre-Calc gang. We're going to start on this third lesson of our limits chapter. This is pretty important and pretty essential when we learn calculus. We'll spend a couple days on this. This is called continuity. Again, with continuity, we have an idea of what that means. A nice smooth curve is a continuous curve, a continuous function. We even earlier started or talked about some types of discontinuities, which we'll also mention here in this lesson. But first of all, this is a really important definition here, so if you need to pause this video to write this stuff down, this is super important right here. Continuity at a point. So rather than looking in this chapter at a function in its entirety to designate whether it is continuous or not, we'll primarily be looking at various points. So any particular function might be continuous at one point and not at another point. And the two types of points obviously we have are interior and endpoints. Interior in the middle of a function, so to speak, and of course endpoints way at the ends. Now, the only way for a function to be continuous at an interior point is this, is if the limit at that point, and again notice this is an overall limit, not just a left or right hand limit, but if the overall limit is equal to the value of the function at that point. So the limit and the value of the function, those have to be the same in order for this to be a continuous function. That's an interior point. Now the endpoints are continuous on the left or the right, and here are the definitions of that. Continuous at the left endpoint if the limit coming from the right is equal to the value, and continuous at the right point if the limit coming from the left is equal to that value. This is a pretty nice visual way. Basically, the idea is if the endpoints are defined and they are at the end of that particular function, then it will be continuous. We'll look at a nice example here on the next slide. But again, make sure to get all this stuff written down. This is pretty essential. Alright, here's kind of a good example. Here we have a goofy looking function up here, as you can see. We're going to look at it in these various spots and try to figure out if it's continuous or not, and we'll try to write in our various reasons here. Alright, so first of all, we'll look at -2. Notice -2 is an endpoint, and it's a filled-in endpoint. So we're going to say that, yes, this is continuous there. And again, just because of what we said before, is the limit, I don't know if I can write this small here, but the limit coming from the left is going to be the same. Let's see, how can I write this? The limit of this function coming from the left is the same as the f of -2 here. In other words, the value of that function. Let me see if I can write that a little bit better here. I'm going to say the limit as x approaches -2 from the right, because that's what it's doing, approaching -2 from the right, is the same as the value of that function. I know what I can do. I can change my pen thickness a little bit. Alright, now let's look at the next one, which is 0. So what's going on here at 0? Well, there is a break in the point here, isn't there? In fact, we call that a point discontinuity. And so we're going to say that, is this going to be continuous? In this case, we have to say no. And again, the idea is because the limit, and this is an overall limit here because we're in the interior point there, the limit as x approaches 0 of this function is not equal to what the value at 0 is. Our limit would be 1, but the value of that function here is actually 0. Hopefully you're starting to get the hang of this a little bit. Alright, let's continue on here. Now let's look at +1. So here the point is defined. This is a pretty classic definition of continuity. It's a nice smooth curve. So this one has to be a yes. And It is, once again, because the limit as x approaches 1 is the same as the value of that function at 1. All right, proceeding onward here, I think I still have some colors that I can use. How about at 2? Now again, here's another kind of discontinuity that we learned about. This is called a jump discontinuity, and so obviously we know that we're not going to be continuous here. And again, I'm going to write this in because the limit as x approaches 2, see if I can erase this little guy a little bit. Yep. Limit as x approaches 2 is not the same as the value at x equals 2. In fact, looks like this function is not even defined at 2. So clearly that would not be the same, and so that's going to be not equal. All right, and lastly here, the very last one at 4, notice this is another endpoint again, but notice the difference on this endpoint. This one is not defined. So in this case, we have to say that no, this function is not continuous over there on the right. And again, we can verify that based on what we talked about before. So the limit in this case as x approaches 4 from the left is not the same as the f of 4. In fact, the f of 4 isn't even defined at all, so clearly that has to be the case. So pretty much common sense type ideas here with this continuity, but the graph definitely helps us here as we look at it. Now let's look at some actual examples with functions. So first of all, the first function, kind of a classic one, x squared minus 4 over x minus 2. Now this looks harmless enough when we graph it. It looks like a straight line, but as some of you figured out, there is going to be a bit of a discontinuity here. Remember, I can factor the top as x minus 2 times x plus 2, like that. Denominator is going to be x minus 2, and sure enough, the x minus 2's will cancel out. So really this looks like the line y equals x plus 2, but there is a little hole in here right at 2. So is this a continuous function or not? Well, this is, we would say point-wise anyway, that this is not continuous at x equals 2. And it's a point or a removable discontinuity is what's preventing it from being continuous right there. Now the next one that we can look at, let's take a look at it. This is one of these piecewise functions again. F of x equals negative x plus 2 when x is less than 1, and x squared when x is greater than or equal to 1. So the first part here, this is just going to be a line, negative sloping line coming in like that, with an open circle here at 1 because of that. Second part is y equals x squared. This will be a parabola with a filled-in circle at 1. So there is kind of a potential break in the graph here. We've seen some where there should be an open circle here, but actually in this case there will be a filled-in circle right at the point 1, 1. And simply it's because of this that our second function here is indeed defined at that point. So that means that this graph is a continuous function, and it's certainly continuous, I think, over the whole function, but for sure we could say that it is continuous at x equals 1. So, kind of interesting to analyze these things at various points. Sometimes they'll be continuous, sometimes not, and good thing to consider. All right, so that gets us started on our continuity. Thanks for watching. We'll see you guys in class.